Let's start. Last couple of lectures we were looking at the characteristics of MOSFETs, and so today and maybe in the next lecture, let's look at how these MOSFETs are fabricated, and so that will take us towards how we carry out layout of the circuits that we design. All right. So now again, of course, there are complete courses on processing, how these devices are processed. So what I'm going to give you is a very simplified view of how MOSFETs may be made, and that presentation is more from the perspective of a designer, not from the perspective of a person who would be actually doing processing. If you were actually doing processing, you would need a lot more details, and so these things have to be discussed in a different manner. So let's go forward and see. So what we have is the technology that I'm describing is a relatively old technology, maybe something like 180 nanometer that we've been talking about. So suppose we have a silicon wafer, which is P-type, and we wish to create. So the first thing about fabrication that you have to realize is that you've seen a MOSFET, you've seen that there are certain regions which are N, certain regions which are P, and so you have to create these regions selectively. So suppose we have a wafer which is P-type and we wish to create a region within it which is N-type. Let's just understand first one very basic fundamental about the fabrication process. So a wafer is given, is P-type, it's already doped P-type, and there is a region in it in which you want it to be N+. So how do we go about doing it? Well, the simplified picture is that to create an N+ region, you need to, let's say if you're using arsenic or phosphorus or whatever dopant you're using, you have to diffuse those dopants into the P-type silicon. Now you can do it by a process called diffusion, or you can do it by implantation. Implantation is where these, let's say phosphorus, they are ions, and then you accelerate them at high energy and then bombard them into the silicon, and depending on their energy, then they'll go and penetrate into the silicon there. And of course, as they penetrate, you'll have a certain profile, and after implantation, you anneal it at a certain temperature to get the proper, to anneal out the damage that may occur, and also to get a proper profile. You're able to do that. In a diffusion, is again a high temperature process, where you have maybe a gas containing, let's say phosphorus, and at a high temperature, then the phosphorus will, let's say, diffuse into the silicon here. All right. So the point is that there are processes by which you can introduce phosphorus or arsenic or P-type or N-type or a P-type dopant into the material. The point that I'm raising is not the details of how those dopants are introduced, but that I want it over only a selective region. How do I do that? How do I do it selectively? So you do that selectively by, for example, by creating a structure like this. Say I have silicon, and I have silicon dioxide which covers it here, and silicon dioxide which covers it here, and this is a window which is open. Now if I do a diffusion or an ion implantation, it would occur here, and these would act as a barrier, right? So it will not go in these regions, but it will occur in this particular region. So the issue is, I can do diffusion and ion implantation, and I can do it selectively, provided I can create a structure like this, a window in silicon dioxide that you see here. So how do we do that? Well, you start with P-type silicon. Now remember, our task is to create a window in silicon dioxide. So you start with P-type silicon, you cover it with oxide. Then what we go through is cover it through an oxide by an oxidation process or a deposition process here. What we go through is a process called photolithography, where this silicon dioxide that you see here, I cover it with a material called photoresist. The photoresist is a material which is sensitive to light. So if you expose it to light, the regions which are exposed to light undergo chemical changes, and the regions which are not exposed to light, they remain as they are. Okay. So a positive photoresist undergoes changes upon exposure, which makes it easier to dissolve in a certain solution. So what we do is we cover it with photoresist, And next, what we do is we put a mask. See, you want to have a certain pattern in the silicon dioxide. You want silicon dioxide to be there at some places and not there in some places. So where you want the silicon dioxide to be there, let's say those regions are opaque. So this is basically, if you can think of it as a glass plate, and these regions are opaque, and this region is transparent. And here I have photoresist. So what you do is you take a mask and you illuminate it normally with a UV light. So the light that you have UV will go through the transparent region and will expose, so this photoresist region will be exposed to UV light. While these regions that you see here, they will be blocked. Nothing will happen there. All right. So this region that you see here, because of exposure to UV light, will undergo chemical change. And its property would be different from the region which has not been exposed. So next what we do is, after we do that, if we put it in a certain solution, then what happens is the exposed portion of the photoresist, the one that was exposed to UV light, that gets removed. And the one that was not exposed, that remains photoresist, because the chemical changes occurred. Right? So you end up getting a pattern like this. Next, what you can do is silicon dioxide, you can etch it in hydrofluoric acid. So you put it in HF for a certain time, and you can etch away the silicon dioxide from here, and the silicon dioxide remains here. And then you can put it in another solution, for example, and you can remove if you want, you can remove the photoresist also. You can remove the photoresist also, and you end up getting a window in silicon dioxide. So how did we get a window in silicon dioxide? Well, we had a pattern on the mask. Remember, certain region was opaque and certain region was transparent. That pattern on the mask, through a sequence of steps, which was basically photolithography, that you see a photolithography and etching of silicon dioxide, that pattern is transferred to silicon dioxide. So what is the point? The point is that if I give a certain pattern on a mask, then there is a known set of steps that can be followed to transfer that particular pattern to silicon dioxide. Okay, a known sequence of steps. I've painted a very simple picture. There are this thing, but a known sequence of steps can be followed to create a pattern in silicon dioxide. Once you have a pattern in silicon dioxide, note that what I can do is, now I can do diffusion or ion implantation, and I will create an N region here. So thereby, I have created a region of N type in a certain place by following a sequence of steps. But what is the starting point? One of the starting point is, where do you want to create that N region here? Do you want to create it here? Do you want to create it here? Do you want to create it here? Where do you want to create that N region? The process engineers, they know how to create that N region. But as a designer, you have to tell them, where do you want that N region? And how do I tell that? Where does that information reside? That information resides on the mask. That information resides on the mask. So once you have, so the general point is, once you have a set of masks, from those masks, if you send it to a foundry, they can take those masks and from there generate your entire set. They know where to create an N+, where to create a polysilicon, where to create an oxide. The masks contain all that information. Okay, and you can create the entire one here. So all right, so so what we are interested in is, how do we create a N-type MOSFET and how do we create a P-type MOSFET? Let's say, to begin with. So note that N-type MOSFET, what we are talking about is a region of N+ here. These are source and drain. We need a thin gate oxide and a poly here. Polysilicon will act as a gate. Polysilicon is also doped. Okay, heavily doped N+ poly and P+ poly here. So these are there. And as I said, this and P+ contact is needed to make a contact to the body, to the substrate here. Okay, so that's the substrate contact here. And as I said, all this region that you see from here to here, all this is the active region. This is where the transistor is made. Any region outside it is all covered with silicon dioxide here. All right, so that acts as an isolation. P-type MOSFET is made in a similar way, except that you have to add an N-well here. So you create a region of N-type region, N-well, and then you do the same thing here, except that these are reversed. You get P+ here and N+ here and all that. All right. So these steps are that you have to transfer the pattern from mask to photoresist. You saw that an intermediate process was, whatever is the pattern that is there on your mask is transferred to a photoresist. That's what we call as photolithography. This pattern on photoresist that you get is eventually transferred to silicon. Right? We created a window in silicon dioxide. And then you do various processing steps, diffusion, ion implantation, or whatever, to create those N regions and P regions and things like that. All right? Okay. This is a simplified view, and this is a view from the CAD tool that we were discussing yesterday, microwave, more accurate, better. These are also schematics, but a better view of how the MOSFET looks like here. Anyway, so let's start with it. Let's start with the fabrication process. So it begins with the silicon substrate. So my substrate is P-type, and there's usually a thin epi layer, let's say, on top of it. Let's say there's a doping of 10 to the power 15 here. These are the wafers that we are talking about. The wafers come in various sizes. You can have 6-inch, 8-inch, 12-inch, different sizes of wafers that are there. A 300 mm wafer, when I say a 300 mm wafer, what I mean is that the diameter of the wafer is 300 millimeters. Okay. 300 millimeters is the diameter of the wafer. So modern processing would be occurring on something like 300 mm wafers, or this. The typical wafer thickness, maybe it varies a lot. In this case, the number that I got from one source is 775 micron. It could be 500 micron, could be 450, but generally, as the wafers are becoming bigger in sizes, the thickness also has to be increased to maintain, mechanical strength. So this is the substrate with which we are starting with. A large 300 mm wafer, 775, let's say, micron thick, and the top surface, let's say, the top surface of the wafer has a doping of, let's say, 10 to the power 15. Now, we want to create both N and P-type transistors, because for the technology that we are talking about is CMOS technology. So almost all the gates that we talk about, ranging from inverters, NAND gates, or whatever, will have an N and a P, both simultaneously. It's a complementary technology. So a P-type transistor, we have to create that as well. So the first thing that I do here, so note that when I'm showing you the fabrication, how things are done, I'm showing you a cross-sectional view and also a top view. On the left-hand side is a cross-sectional view. On the right-hand side is the top view. So P-type transistor is created. We need to create a P-type transistor. So what I need to do is I need to create a region which is N-type, N-well. All right, N-well here. So this is a cross-sectional view. And this is the top view. This shows that, so I have to specify that I need a region of this much area in which I'm going to make a P-MOSFET here. So now note that I have to create this N-well at a selected places. Wherever you want a P-type MOSFET, you will have to create an N-well. Right? So as a designer, what do you have to specify? There will be a mask called the N-well mask. And as a designer, you have to specify this area here. On your mask, you have to specify where do you want this N-well and of what size. What size do you want? Okay, so this is the job of the designer, to specify this particular part here. This is where the N-type MOSFET. Now, what size and all that will come to later on. How do you decide sizes and all that? Okay. The next thing is, so once you create an N-well, you define the active areas. Regions which are active, which means where the transistors are going to be fabricated. So that's an active area. And as I said, anything outside the active area is all covered with silicon dioxide as isolation. So active area, for example, all this, so I'm defining that this is where I'm going to create my N-type transistor here. And the region outside, or all outside here. So for example, this is the cross-sectional view. The top view is like this. Note the active area. This is the active area. This is where I'm going to make my P-type MOSFET. This is another small active area. Right? So active areas are what? The areas which are not covered with silicon dioxide. So in this region, you have the normal silicon wafer that is there, P-type, or in this case N-type, because this is inside the N-well. All right, anything outside is all silicon dioxide. Anything outside active area is all silicon dioxide. The surface is not exposed anymore. In this region is where it is exposed. So why did I keep it like this? If you note, so this is where, for example, I'm going to create an N plus region and an N plus region, and I'm going to create a N-type transistor. And this small active region is where I'm going to create a body contact to the body. So deliberately I've kept it separate here to show that this is for creating the body contact. And here I'm going to create a body contact to the P-type MOSFET. And this is the body contact for the N-type MOSFET. All right, so separately. shown here. All right, so we need a mask to define which are the active areas, because you have a certain pattern here. This is the active region here. This is the active region here. This is the active region here. Active region here. You need a mask to define that. All right, so suppose we have done that. The next thing that we do is we define the gate of the transistor. The gate is defined first. Source drain are defined later on. So what we do is, for example, let's say, for example, so typically what would happen is that the whole, note that this is silicon dioxide, but this silicon dioxide and all that is for isolation purpose. It's not for making a transistor. It's pretty thick and it's not of that high quality. While here, what would happen is a very thin layer of silicon dioxide would be deposited, of very high quality silicon dioxide, because that will act as a gate insulator. On top of that, polysilicon will be deposited, and then you will etch away polysilicon and gate oxide from everywhere else, and you'll leave it here. So I've not shown here the silicon dioxide, but underneath polysilicon, note that there's a thin gate oxide. That's how you create a MOSFET. So there is polysilicon and there is a thin gate oxide, and then there is this one here. All right. So, but from a designer's perspective, all you need to do is specify where do you want the poly. Wherever you would put the poly in the active region, during the processing, under that active region, under the poly, the gate oxide will be put. Okay. So note that. So I have to specify this is where my gate is going to be. So gate for P-type and gate for N-type. So this is cross-sectional view. Top view is like this here. This is where my gate is. Now note, look at this particular poly here. If I look at this poly within the active region, underneath the poly, what is there? Thin gate oxide. But note that poly extends beyond the active region also. So under this poly, what is there? Outside the active region. See, poly, I extended it beyond the active region also. So what is there outside the active region? By default, silicon dioxide. The surface is covered with silicon dioxide. So with the thick silicon dioxide, okay, for the purpose of isolation. So this extra polysilicon, the extra poly that you see here, where is it running? It's running on top of thick silicon dioxide. But the moment it comes into the active region, this polysilicon now is running on top of thin gate oxide. All right, so just keep in mind, this polysilicon versus this polysilicon here. Where is it running? Okay. So I create a polysilicon here and polysilicon here. The next thing is I do my ion implantation or diffusion to create an N region, N diffusion here. Now note that I need a mask here, which is called a poly mask, because I have to do polysilicon selectively here and selectively here. Anything that you have to do selectively, you need a mask. Without that, you can't do it. Okay. So next you do is N diffusion. So what you do is you select the areas where you don't want the diffusion and leave the remaining regions here, and you do an ion implantation. So ions, N plus ions will go there and you'll get that region. So note that we call it an N diffusion mask or a P select mask, N diffusion mask here. So we select a region here where I create N plus here. So I create N plus here and I create N plus here also, because the body of P-type MOSFET is N-type, so I need an N plus here. So note that N plus goes here, N plus goes here, N plus goes here. And note that what I'm showing it is a mask like this here, dotted mask here, which is called P-select mask. So what I'm doing through this masking step is protecting these areas. I'm protecting these areas and I'm protecting these areas, and then if I do ion implantation, it will go only in these regions. We'll create these N plus. N region here, N region here, N region here. All right. Otherwise, the rest of the regions are protected. So that's how. Now note that I've already created an N-type transistor. I have N plus here and a polysilicon gate here, except that I've not created a body contact. So next thing, we do the same thing. We do P diffusion or an N-select mask. So we cover this up, and we do P-type implantation. And so I get a P plus here and a P plus here and a P plus here. Our transistors are ready. N-type transistor is ready here. Source drain, body contact. P-type transistor here with a body contact. The transistors are ready, but they're not useful. I have to make contacts to them. So what I do is, next, note that after you make this, the whole region is again covered with silicon dioxide. After you've done all this processing, poly and N plus and P plus and all that. Everything is covered with silicon dioxide fully. All right, and then wherever you want to make a contact, you cut a hole into that particular silicon dioxide. You cut a hole into the silicon dioxide here. Note that everything is covered with silicon dioxide by default, the whole thing. And then you cut a hole into it, and this is what, so these are called contacts. So I need a mask again, which defines where do you want to make a contact. I want to make a contact here. So this black thing that you see here is for making a contact. So I have to define, there is a separate mask called contact cut mask. So I define this black region here, black region here. So I'm going to make a contact here and here for source drain, and I'm going to make a contact here for the body, and I'm going to make a contact here for P-type, and again body here. So I need another mask for defining these. Once it's done, then I need the first layer of metal now. It's called the metal 1 mask. Suppose I want to connect, if I'm making a CMOS inverter, I want to connect the drain of NMOS and the drain of PMOS together. So what I do is, again, so what would happen is the whole surface will be covered with a metal, and the metal will be removed from places you don't want, and wherever you want a connection, the metal will be retained, and that's how you end up connecting this one here. And look at from the top view. So I put a metal here, and the metal has to be on top of the contacts. Then only the metal has to cover the contacts here and cover here, and that's how you end up creating, joining the two drains together. So thereby we have now created an N-type transistor, a P-type transistor, and we have connected them up. Now, one layer of metal is really, it's not enough to connect all the devices together. So what you do is you cover it with another silicon dioxide. I'm not showing. So this first layer of metal will be covered with silicon dioxide, right? And then on top of silicon dioxide, what will you have? The second layer of metal, right? So second layer of metal. And how do you connect the second layer of metal to the first layer of metal? Well, you need a contact again. And those contacts are all called vias. So the first one, the first contact is called, we call it the contact mask here. After that, any subsequent, when you need to connect metal 2 to metal 1 or metal 3 to metal 2 and all that, you need a via and you need a metal 2 mask. So, this is a kind of a picture that we have. The first one is the contact to the source or the drain and the first layer of metal. Then in between first layer and second layer of metal, what do I have? Silicon dioxide again. And what are these masks? These are via masks. So I need a via here to connect them together. I need a via here to connect them together. Via here to connect them together. So I have metal 1, 2, 3, 4, whatever number of, in modern processes, you may have 8 to 9 layers of metal that you see there. Okay, so now the thing is, you've seen that to do the fabrication, I need a set of masks. And who has to specify these masks? The designer, right? And how do I decide, for example, what sizes of the end-well to choose, what sizes of the some of these things that you see here, what should be the dimensions? So, where will these dimensions come from? Some of them come from, of course, as a design. When you have designed a MOSFET, you've decided already the width of the MOSFET and the L of the MOSFET. Depending on the circuit, if I'm designing a CMOS inverter, let's say I decide N-type transistor will be 2 micron by 1 micron. Width is 2, length is 1. And P-type MOSFET is, let's say, 4 micron by 1 micron. So this is a part of the design that you come up with the widths and the lengths. But the widths and the lengths are not enough information. The other information that comes from is that when you have to do the drawings, these are literally what we are talking about is geometrical drawings. Basically a series of rectangles of different dimensions. So you're talking about geometrical drawings. So when you do these drawings, you have to obey certain rules. It's not that arbitrarily I can choose an end-well of any size that I want, right? So there are a certain set of rules which we call design rules here. And the aim of these design rules is that if you obey them, the foundry guarantees that that whatever your design is can be fabricated with reasonable yield and without errors. If you violate those rules, there's no guarantee. Some transistors may end up not working. Okay, so based on experience and based on, we'll talk about it, based on the kind of limitations that are there of the processing, a set of rules have been crafted so that your design becomes manufacturable. Okay. These design rules come through interaction of there are electrical considerations, there are reliability considerations, there are limitations of the fabrication process, which all come together to define what those rules are that you have to obey here. For example, let me show you a few rules that are there here. So the rules that I'm going to talk about will be described in terms of a parameter called lambda. The rules, we call those rules as scalable design rules. You'll see in a minute why. So if I specify all the rules in terms of a parameter called lambda, what would the rules actually be? Note that we are talking about geometrical drawings. The rules would be what? The rules would be what should be the length, what should be the width, what should be the area. So we're talking about dimensions, right? So if I describe dimensions in terms of lambda, now what is this lambda? Okay, so these are simplified rules. What is this lambda? So lambda is determined by the technology. In a simplified view is, suppose I'm using a 1 micron technology, then lambda for 1 micron technology would be 0.5. So if any rule I specify anywhere as, let's say the width of your polysilicon, minimum width of polysilicon should be 2 lambda. Suppose I specify the minimum width of polysilicon is 2 lambda. Now what does this mean, 2 lambda? Well, it depends on the technology. If I'm using a 1 micron technology, then lambda is 0.5 and therefore the width is 2 lambda, which is 1 micron, right? So why do I call it scalable design rules? Because if I specify everything in terms of lambda, it's very easy to go from one technology to the next. Rules remain the same. It's still 2 lambda, 3 lambda, 4 lambda. All that you have to do is just change the value of lambda. That's it. Okay. All right. So look at these rules. Some of these rules are shown here. Now the rules will be for various layers that are there. For example, we saw polysilicon. Polysilicon is what defines the gate. So there's a rule which says that if you have a polysilicon wire running, the minimum width of the polysilicon wire is 2 lambda. Everything is in terms of lambda, 2 lambda. And the minimum separation between 2 poly wires has to be 2 lambda. That's one rule. You cannot violate that. If you try to draw 2 poly lines which are closer than 2 lambda, chances are that some errors will occur in fabrication, your design will not work. You have to obey that particular rule here, right? So this is a rule about the dimension of the poly wire, and this is the spacing. All that it says is these are the minimum dimensions. 2 lambda here and 2 lambda here. You can make it 3 lambda, 4 lambda, 5 lambda, whatever you want. Similarly, you can make this as large as you want. There's no rule on that, but there's a rule that minimum is been specified. Similarly, there's a rule. Metal 1 has to be only 3 lambda. Minimum is 3. And the separation between 2 metal 1 wires is again 3. You can't make metal 1 which is 2 lambda. All right, so that's another rule. Contact. Remember the contacts that are made. So the minimum dimension of the contacts or the dimensions of the contacts are 2 lambda by 2 lambda. You can't make a contact which is 1 lambda or this. So these are there. This is the active region here. So rules for example, N plus. So when you have an N plus wire, it says the minimum length of an N plus wire, N plus source, minimum width of the N plus source is 3 lambda. And minimum separation between 2 N plus is 3 lambda. This is the well. It says minimum dimension of the well that you can have is 10. If the wells are minimum dimension is 10. If they are the same potential, 2 wells can be 0 lambda, which means that they can be touching each other if they are the same potential. If there are 0 or 6, I have to check why this is 0 or 6. Why 2 of them are specified. Different potential, then the minimum separation has to be 9 lambdas here. So like that, you can see here, there are various rules that you have to obey while doing all those drawings that are there. Okay. And so this is the rule for transistor, for making a transistor. Note that this region is N plus. And as I showed in the last lecture also, and this region is poly. And wherever the N plus and the poly intersect, this is where you get a transistor. All right, this is where. Now, the rule says the following, that the poly that you see here must extend beyond the N plus region by at least 2 lambda. See, you want the transistor only till here, right? But so normally you would think, well, let me bring a poly only till here, till this particular point, and that's it, stop. But what is the design rule saying? Well, you have to take the poly and extend it beyond it by at least 2 lambda. Why is it saying it? It's easy to understand this particular rule. Why is it saying it? Suppose you draw this only till here, till this region here, poly. Okay? And n plus is here. Now remember, which one is, so what would happen is, the fabrication process is not perfect, right? So let's say you've drawn it till here. But what due to error, if some error, it goes here, a little bit towards the left. What will happen? Little bit towards the left, what would happen then? When you see after the poly, what do? You do n plus diffusion. So if this poly goes little bit towards the left here, there would be a region here exposed, active region here, and when you do n plus, you'll get n plus here, and in this n plus here, and then n plus here. You'll be a short. A short will occur. The source and the drain will get shorted through the n plus region. So you cannot keep it perfectly at this particular point. You want a transistor right till that particular point, fine, but you can't keep it here because there are errors. One cannot do anything perfectly. So this edge may move left, or if it may move right. If it moves right, it's okay, no problem. But if it moves left, there will be an exposed region where I will get n plus and the source drain will get short. And for that reason, the manufacturer is telling, well, when you draw a poly, please extend it beyond that by 2 lambda. So the manufacturer is sort of guaranteeing that there may be an errors in my fabrication process, but if you extend it by 2 lambda, it's not possible that this edge will again come back by 2 lambda. That much error I don't have. Okay, so it will not, this edge here may go left and right, but it will not come back so much that a region will get exposed and the transistor source and drain will get short. So the rule is coming because of, in this case, because of the limitations of the fabrication process, because of the errors that are inherent in it. And similarly, there are other rules. It says you must extend the n plus region beyond it by 3 lambda. You must extend it beyond by 3 lambda. When you have an n plus region, you cannot arbitrarily change the geometry of the n plus very close to the poly. You must extend it by n plus, don't change the geometry. After that, at least by 1 lambda. After that, do whatever you want. You want to make it larger, smaller, whatever you want, you can do it. But till, whatever is the geometry here should extend at least till 1 lambda. Then make the changes. Right? So you can see all these rules that are there. If this is the boundary of the well, then it says it should be away from the well boundary, these n and all these regions, by at least 5 lambdas. These things should be away from it by 5 lambda. All right, so like that, there are rules you can see here, VR rules, metal 1 to metal 2 and all that. So I'll leave it for you to think about those rules. And for now, there are various other rules here that are there. Let me give you, I talked about why, for example, a certain layer has to be extended, but let me give you, for example, one of the rules were, if you go back and see, that the two diffusions, n plus diffusions, let's say source and drain via source and drain diffusions, have to be separated by 3 lambda, at least 3 lambda. All right. Let's look at, for example, how do I create two diffusions, n plus diffusions, and why do they have to be separated by a certain length here? All right. So as we said, fabrication process is not perfect. Fine. So suppose these are two n plus diffusions, right? N plus here and n plus here. And we are saying the rule is that you must keep them separate by at least 3 lambda. When you draw them, you must keep them separate by 3 lambda. Now, why is the manufacturer saying keep them separate by 3 lambda? The manufacturer is saying that because if you don't keep it by 3 lambda, normally when you have this n plus and then this n plus, two n plus regions, you don't want any interaction between them. You don't want them to get shorted together. Plus, you don't want any, this region should be electrically isolated from this. You may put a potential of 5 volt here, 3 volt here. One should not affect the other. So let's look at, suppose I want to create these two regions, which is n plus here. Where are the errors that can occur here? So this sort of shows you the possibilities of errors that are there. Remember how these n plus is created? You have to create a window in silicon dioxide. So now, let's say you have specified that this window is of this length, and then there is an opaque region, and this window is of this length, right? But when you shine light through it, you know there's diffraction. So the light doesn't go straight in line here and expose only this part of the photoresist. The light will also expose a little bit along the corners also. So even though you specified a length of, let's say, 1 micron, the effective region which gets exposed may be a little bit longer. Depending on the wavelengths of light and all that, the region which gets exposed is a little bit longer here. Right? Now, after that, you have to remove the photoresist. Now, when you remove the photoresist, you think whatever chemical is removing the photoresist removes it vertically like this. You know, when you put it in a chemical, it starts etching away laterally also. Not only that, after that, when you etch the silicon dioxide here, you think hydrofluoric acid, when you put it, it will etch vertically. As it starts etching, it starts undercutting also. It starts, cutting sideways also. So what ends up is, you wanted a window of this much, and what do you end up getting? I'm exaggerating, of course. You end up getting a window not of this much, but of this bigger size here. Because the etching of silicon dioxide is not vertical. So it becomes a little bigger here. The similarly removal of photoresist is not vertical, so it becomes a little bigger here. So what did you end up getting? You wanted a certain spacing between the two these two windows. The spacing has become smaller. Now, after that, when you do an N plus diffusion, you think when you do N plus implantation, it will just go vertically underneath it. Because after you do the implantation, the ions are going into it. The ions go also sideways. And then when you heat it up, when you anneal this particular substrate to remove the damage, the N plus penetrates laterally also. So N plus penetrates laterally also. So remember, you were thinking as a designer that this would be the effective separation between these two N plus regions here. After the fabrication process, what is the effective separation here? Much smaller. The effective separation between the two N plus regions has become much smaller. Now there is another problem. The N plus is being created in P-type region here. So there's a depletion region associated with this P-type. There's another depletion region associated. If they come very close to each other, the two depletion regions may merge. And when they merge, the two N plus regions get electrically coupled together. Any change in potential here may reflect in a change in potential here. So you're saying because of these electrical reasons, because of all these imperfections in my fabrication process, the etching and the exposure and things like that, there's a minimum spacing that I must maintain. If I don't do that, the two N plus regions may get uncomfortably close to each other and things will not work. And for that reason, I must maintain a certain separation. Okay, so this tells you that I must maintain a certain separation. How much separation and all that we cannot talk about. That depends on the details. Okay, that details of the fabrication process here. All right, so in the remaining time, let me now step by step do a layout for a inverter. So we have not done a CMOS inverter, but this is how it will look like. A NMOS transistor here and a PMOS transistor. And let's say after doing the design, we'll go through the design later on. After doing the design, we come up that the size of the NMOS inverter is 3 lambda by 2 lambda. 2 lambda is what? The length of the MOSFET. And 3 lambda is the width of the MOSFET. And 6 lambda is the width of the P MOSFET. And 2 lambda is the length of the P MOSFET. Okay. So this is a CMOS inverter. This would be a common source amplifier. Common source amplifier. I will apply my voltage here. So this is my drive transistor. And I'm using an active load. Active load is P-type. If you recollect your E210, we were doing NPN transistor here, and a PNP active load is the same thing. NMOS transistor here with a PMOS active load here. So the two things are very similar, as you can see here. In one case, I short them together and it becomes an inverter. In the other case, I apply an input here, there is a fixed bias voltage here, and this becomes a common source amplifier. All right. So when you finish with your design, you will typically have the sizes of the transistors available to you. So 3 lambda by 2 lambda, 6 lambda by 2 lambda. So with these designs, you've already done circuit simulation. You've already checked, well, it gives me all the right things that I want. So the next step that you want is, well, let me now do the layout as a designer. Okay. So layout means, as you can see here, the relative drawings for the different layers that are there. And we have to decide where to put the transistors, how to interconnect them and all that here. Okay. So let's do the layout here. So we're going to make the NMOS first. So step-by-step layout of a transistor. So from the layout, from the designer's perspective is what? If I want to create a transistor, I have to create an N plus region and I have to create a poly. That's it. A transistor is created. Okay. So note that I have to create a transistor. Go back here and see NMOS transistor 3 lambda by 2 lambda, right? 3 lambda by 2 lambda. So what do I do? 2 lambda is what? Gate length. So I choose what? The poly here width is, I choose 2 lambda. And I draw a poly wire like this here. And this one is 3 lambda, right? The width. So I choose the width here, 3 lambda of the N plus here. So I draw this N plus region here, this one, 3 lambda, and I draw this here, 2 lambda, and I get a transistor. Where is the transistor? In this intersection area here, right? This is where the transistor is. Transistor is in this region here. That's it. Now, what other rule did I obey? There's a design rule which we just saw, which says extended by 2 lambda. So I looked at the design rule, and the design rule says poly must extend beyond this by 2 lambda. So that's why it is extending. Okay. I don't know what is the length of this particular N plus now. I don't know as yet. Okay. Make the contact between ground and source of the NMOS. Remember this point is ground. Keep this thing in your mind here. NMOS is connected to ground. PMOS will be connected to VDD. Okay. And the body of the NMOS is also connected to ground. And the body of the PMOS is connected to VDD. So keep that picture in your mind while we are doing the layout. So make the contact between the ground and the source of the NMOS. So source is here. I'm calling this as the source and this the drain. I have to make a contact to the ground. Right? This is what I have to do. So what I do is, this is how I make a contact. First of all, my contact that you see here, I say that this is a piece of metal here, metal 1. This wire, I'm going to call it as the ground here. And this N, that region that you saw here, I extended it over here. This entire region, I made it N. Now note that this entire region is N. And on top of the N, the metal is running. Please keep in mind, on top of the N, the metal is running. Why? On top of the N, what is actually there? Silicon dioxide. On top of the N region, what do I do? As I said, after you do N plus, P plus and all that, you cover the whole thing with silicon dioxide. So actually, after this green region that you see here, N plus, is covered with silicon dioxide. And on top of silicon dioxide, what do? I run a metal like this here. Blue metal 1 running here. And I make a contact here at this contact dimension that you see here. So what will happen is, this metal 1 and the contact are connected together. And at the contact, what happens? The contact goes through and makes a contact to the N plus here. And there are rules for the contact. The rules are of whatever dimensions and whatever. These are all rules here. So I get these dimensions, the spacing we just saw has to be minimum of 1 lambda, and all these rules are there, that the contact must be away from it by 1 lambda, 1 lambda, 1 lambda here, and minimum dimension should be 2 lambda here. So I get these dimensions from here, from the rules. The rules specific, because I don't want to make my N plus region unnecessarily large, because that would occupy more space and maybe add more capacitances. I don't want to do that, right? So I want to use minimum dimensions. And where do I get minimum dimensions? From the rules. They tell me what the minimum dimensions of each one of these layers are. So at this stage, I've created an NMOS transistor, and I've also created a connection to the ground. Right? This metal, go back and see where are these metals. Look at this metal here, metal 1. Right? So this is my N plus. In between, what do I have? Insulator, let's say it's silicon dioxide, and metal 1. And this is the contact that I'm talking about. Okay? In our picture that you see here, there's a silicon dioxide here, there's the contact here. So the moment you specify that I want a contact of this dimension, in the fabrication process, well, a sort of a hole will be cut into the silicon dioxide, filled with metal, and it will come and make a contact here. So you don't have to bother about those. That's what I said. But you have to specify where do you want to make the contact. As a designer, you have to specify that. Okay. All right. So let's go back to our. So we have already created. Now note that NMOS is not complete. I have to make a substrate contact. There's a substrate body contact. So now I'm showing it explicitly. So what I do is this. Where will you create a body contact is again up to you. So what I did was I created this region here. Here, this is what, now note the different color. The green color typically is for N plus region. The orange or this kind of a color is for P plus. So this is the region where I do P plus. And this is the region where I do contact. And you are not seeing it, but we are extending the this metal here that you see here blue. You will not see it. The metal is extending here also. So this metal that you see here is extending all the way like this here and coming here. This metal is going. And this is where I have P plus also. And this is where I have the contact also. And thereby I've made a contact to the body. Body is P type. And I created a region P plus. And I made a contact here. And this region is covered with this metal here. And thereby I've made a contact. Yes? Separate contact. You have to make a contact to the body. Now, in this case, as you can see here, is the same metal line which is making a contact to the body. So the body and the source are shorted together. On the other hand, if I didn't want body and source to be shorted together, this body that you see here, I could have separately made somewhere else here and use a different metal, which is not ground, but some other body contact. Okay. The drain of, now note, the drain of NMOS has to be connected to the drain of PMOS. I need a connection here, right? The drain of NMOS has to be connected to the drain of PMOS. Now the drain of NMOS is what? Drain of NMOS is N plus. And the drain of PMOS is what? P plus. I can't simply connect them up. So what do I need? I need to make a contact. Metals. So note, I made a contact here. This region that you saw here, I extended it here. And there's a metal here. So note that the metal always covers this contact. This contact that you see here, this blue metal is covering this here. Then only you can make the contact between the metal and the N plus. So the metal is there, underneath N plus is there, and in this region, that hole is there, which is filled with, again, metal, so making a contact. So now I've made this contact here, with this metal here. So now my NMOS transistor with a body contact, with all this is available here. But I've not made a contact to the poly also, I'll make it later on. So next, the PMOS transistor has to be drawn. Okay, so let me do it quickly now. So PMOS transistor, there are rules that how much you have to extend 5 and all that. Now PMOS has to be made in a N-well. So this is the edge of the N-well. There are rules that, the N-well edge must be away from the N plus region by 5 lambda. So now N-well is there. And this is the N-well edge. And now I make similarly the PMOS transistor. Note, very similar, but it's of a different dimension. The dimension here is 6 lambda. Because PMOS was 6 lambda. Dimension is different. And this is VDD. Minimum is 4 lambda. Minimum dimension of this is 3 lambda. I've chosen it 4 lambda here. And this is there. Next, let me add a body contact here. Body contact is also added. Now, this is the N-well where the PMOS is fabricated. I have to connect now the two of them. So the poly is taken here and connected back here, and I make a contact to the poly and I bring it out in the metal. Right? Now my layout of an inverter is ready. My inverter is ready. I can apply an input at this place. I can apply an input here. I can take an output here. This is the line which is running for ground. This is the line which is running for VDD. Right, so my layout is ready. Now you can do an analysis of your layout. The first analysis that we usually do is, let's put a box here which completely encloses your the inverter here. Minimum size rectangular box which completely encloses is here. The area of our inverter, once you go and look at it, is width comes out to be 15 and the height comes out to be 45 lambda squared. So area comes out to be 675 lambda squared. Aspect ratio, height versus width, 3 times taller as compared to the width is 3 by 1. Now that's not the only way. You can make aspect ratio maybe 2 by 1 by adjusting things. You may even make it 1 by 1. There may be a requirement. So the drain area, now you can calculate how much is the drain area. You can see that this whole region is the drain area. Drain area you can calculate is 19 lambda square. The perimeter of the drain, all this drain is here, perimeter of the drain you can calculate is 15 lambda. For the NMOS and PMOS and all that you can calculate. And why do we need this? Well, area and all that of course are important. We need this drain area and the perimeter. Why? For the capacitances. So once you have the layout, these areas are needed to put it back into our schematic, because now with these areas we can calculate how much is the source to body and drain to body capacitances. So the areas are needed to put back there, and more of this. So we'll discuss that in the next lecture. All right, so let's start.